Okay, so good afternoon, everyone. Today, I'm here to present my master's research on QuAC, Quick Attribute-Centric Type Inference for Python. So Python is one of the most favorite programming languages since 2018, surpassing longtime favorites such as Java and C. However, unlike these languages, Python is dynamically typed, which facilitates rapid prototyping and makes it particularly popular in fields such as data science and web development. However, with the rise of Python, we also see the rise of the disadvantages of dynamic typing, such as these pesky runtime type errors, which you may be familiar with. In contrast, static types enable more meaningful static analysis, error checks, and refactoring passes. Thus, in 2014, PEP 484 introduced Python type annotations, which are not checked by Python itself, but are used by IDEs and static type checkers to check the code before it runs. However, despite the advantages of Python static type annotations, only a tiny proportion of Python code is actually annotated. This 2020 study estimated only about 4% of Python code is actually annotated. The clear advantage of type annotations, but the apparent reluctance of developers to add them, has led to the development of several type inference tools that aim to reduce developers' burden. A good type inference tool should output as many type annotations as possible, achieving high coverage. In addition, its predictions should be correct, achieving high accuracy. Furthermore, it should be performant and should not run in too much time. Static type inference methods utilize rule-based approaches, data flow analysis, and heuristics to create and solve typing constraints. They aim for correctness and achieve high accuracy with simple types in limited contexts. Machine learning-based methods use natural language queues with various machine learning models. They can handle the complexities of Python and can improve coverage. However, they face out-of-distribution generalization challenges and cannot guarantee type correctness. Furthermore, they may incur significant performance issues, such as immense requirements for computation and energy, especially for large language model-based methods. Thus, finding a balance between coverage, accuracy, and performance remains challenging. Let me present an example that existing approaches struggle with. In the code on the left, the global function maximize has the parameter points and the return value element. The industrial static type inference tool PyType does not make predictions for points and predicts elements to be the trivial any. The state-of-the-art academic static type inference tool Stray does not make predictions for both points and element. The state-of-the-art non-LLM machine learning-based type inference method HiTyper predicts points to be tuple, which is technically correct, but is over-constrained, as points could also be lists. In addition, it does not predict the type parameters of tuple. Furthermore, it predicts element to be string, which is wrong. Last, the recent LLM-based type inference method type T5 predicts points to be list, which is also over-constrained, as it could also be tuple, and it does not predict lists type parameters. It does make the correct prediction for elements, though. However, this is a good example that showcases the power of our type inference tool, QuAC. So QuAC determines the type of variables based on the attributes that are accessed on them. In the global function maximize, we can observe that the parameter points accesses the iter method for iteration on line 10 and the getItem method for indexing on line 9. Thus, it has the attribute set iter, getItem. Based on this attribute set, the parameter points could be something like a list, a tuple, etc., and Python's typing module defines a sequence particle that covers all such cases. And our method, based on this attribute set, can correctly predict that points should be of class sequence. Now, sequence is a container class with a type parameter t. And QuAC then can predict it to be the user-defined class point. We'll get to container type parameter prediction later, but for now, sequence of point is the most generic correct type here. Furthermore, for the return value, the case is a little more simple. The return value calls its method maximize on line 11. Thus, it has the attribute set maximize. If the user-defined class point is the only class within this context providing this attribute, then element should be annotized with point. QuAC also correctly predicts its type to be point based on the attribute set. In the upcoming slides, I will first introduce QuAC's core approach before showcasing the highlights of our evaluation and discussing remaining challenges to be addressed. First, I will start with QuAC's core approach. So given an attribute set for an expression, QuAC first predicts its class. QuAC chooses its class from a class query database, which QuAC constructs as follows. The class query database includes built-in classes such as int and list, protocols from the Python standard library such as the sequence, classes from imported external modules, as well as user-defined class such as the point. Then, given an attribute set, QuAC must select the best class that provides those attributes. For example, in the example that we've showcased before, many classes such as typing point sequence, typing point mutable sequence, as well as a built-in list, all provide the attributes iter and getItem. To rank these candidate classes, QuAC uses information retrieval techniques similar to what a search engine does. Specifically, it uses the BM25 ranking function, a standard information retrieval heuristic, to rank candidate classes. The score of a candidate class is as follows. So in this formula, we consider all the attributes in the attribute set, the IDFs or rarity of those attributes on all classes, the frequency of attributes within that candidate class, which is either 0 or 1, depending on whether the attribute is absent or present, as well as the candidate class's length in relation to the average class length. So with the BM25 ranking function, we can prioritize rare attributes and the smallest class that satisfies an attribute set. And if the predicted class is a container like sequence, QuAC then predicts its type parameters. In the example that we've discussed before, QuAC predicts the class of the parameter points to be sequence. Now, sequence is a container class with a type parameter t. To infer t, QuAC first determines the semantics of t, which we represent with the relation set value of, iter target of. This means that t has the types of the values stored in a sequence object and the types of the elements iterated over a sequence object. In the source code, we notice that element is a value that is being accessed on points, and p stores the value that is being iterated over points. Thus, based on t's semantics, we can conclude that it has the attributes of element and the attributes of p, leading to the attribute set of maximize. Based on this attribute set, we can predict the class of t to be point, which is not a container, so we conclude that the type of t is also point. We fill in the type variable t and predict the type of parameter points to be sequence of point. In this process of predicting container type parameters, we have used the concept of relations. First of all, we use relations to model the semantics of container type parameters. For example, in dict kv, the relation set of the parameter k includes key of and iter target of, suggesting that k has the types of the keys stored in a dict and the types of the elements iterated over a dict. In comparison, the relation set of v includes value of, suggesting that v stores the types of the values in a dict. In addition, we also use relations to associate potential container expressions with semantically related expressions when we analyze source code. For example, given the for loop for x and y, we record that y is iter target of x. And given the indexing expression x indexed by y, we record that y is key of x. And x indexed by y is value of x. This procedure allows us to recursively predict container type parameters. This finishes our introduction of QuAC's core approach. We will now discuss our evaluation. To evaluate QuAC, we compare it against state-of-the-art baselines, such as state-of-the-art non-LLM methods, including stray as static type inference method and HiTyper, a machine learning-based type inference method. We also compare against the recent LLM type inference method, type T5. We use popular real-world Python projects in our evaluation and use MyPy, a type checker, to check the correctness of the predicted type annotations to measure our accuracy. We also compared against the ground truth type annotations on the typed benchmarks in our paper, but we are not talking about that now. So we compared QuAC against the non-LLM benchmarks in terms of coverage in this graph. Stray is the blue bar, HighHyper is the red bar, and QuaC is the yellow bar. When compared, QuaC and HighHyper are similar in coverage as measured by the number of non-trivial type annotations which are not none, which are not object, and which are not any, with QuaC further leading on several benchmarks, such as Peewee, Seaborn, Sphinx, and Workzog. Regarding accuracy, QuaC also consistently outperforms Stray and HighHyper across most benchmarks. Though Stray does achieve high accuracy on some benchmarks, it makes much fewer type predictions and fails to make any predictions for a lot of the benchmarks. Regarding performance, QuaC also vastly outperforms Stray and HighHyper on almost all benchmarks with an average runtime reduction of 15 times. These data show that QuaC excels at balancing coverage, accuracy, and performance. When compared against type T5, the LLM-based method shown by the green bars, though type T5 predicts 1.9 times more non-trivial type predictions on average, it also incurs a significant runtime cost, with type T5 being nearly 2 orders of magnitude slower than QuaC. Thus, we can still say that QuaC excels at balancing coverage, accuracy, and performance. Now, let's compare QuaC against the baselines in predicting container type parameters. So the annotation list of int, where we have the type parameter filled in, is much more useful than simply the class list, where we don't have the type parameter. When compared against the non-LLM methods, QuaC predicts many more type parameters on a majority of the benchmarks. And it also does so at a higher overall accuracy. This demonstrates the effectiveness of QuaC's approach to predicting container type parameters. However, what's interesting is that when compared to type T5, QuaC predicts a higher number of parameterized containers on the untyped benchmarks, while type T5 does better on the typed benchmarks. This shows that there is a clear distribution shift affecting type T5, depending on the presence of type annotations in type T5's pre-training data. We used a two-tailed t-test to analyze the difference and found out that there was no significant difference for QuaC, while there was a highly significant difference for type T5. This shows that when compared to type T5, QuaC is significantly more consistent in predicting container type parameters. Finally, I will discuss a remaining challenge. QuaC fails when there are too few, too unspecific attributes. For example, in this function, the parameter s is only involved in 2 multiplication operations. Its attribute set only includes one attribute, mo, implementing multiplication, and occurs in both numeric and sequence types. Given the single attribute, it is challenging for QuaC to decide that s should be stir, a conclusion that can only be reached by considering the natural language cues, such as the function name, as well as the names of the variables. Thus, a meaningful research direction would be to include QuaC as part of a hybrid LLM symbolic method. This enables using LLMs to leverage natural language cues. On the other hand, including QuaC also has the potential to improve performance and mitigate the training data bias when compared against a pure LLM-based method. So this concludes our introduction of QuaC, Quick Attribute-Centric Type Inference for Python. We hope you enjoy the talk and feel free to scan the QR code to access our paper and our GitHub repository. Thank you, and I look forward to any questions.
Questions to the mic, please.
Hi, Arjun from Northeastern. Thank you for the talk. Very cool work. Python is like worse than you described. What I'm thinking of is things like, it's not just classes, but people do things like just use dictionaries and pass them around. And if you're very good about typing your code, you might sort of use things like type dict. I understand that this is like beyond the scope of what you're doing, but any thoughts about that?
Yes, so I guess the modeling for a typed dict could follow a similar pattern for the modeling of things like container type parameters. So for container type parameters, we defined relations which associated the semantics of the type parameters with expressions in the code. And for things like typed dict, we may have similar syntactically defined rules that says when we have a dict-like expression and we access certain fields on it, especially using string literals as the keys, we may record those keys as potential members of the dict. So this may be a future research direction that may help in predicting things like type dict.
Cool. So one very quick question. So BM25 has a bunch of parameters that you can sort of play with. Did you do anything with that?
Not at the moment. So I just used the default reproduction package.
Okay.
So, but I could explore that in the future.
Hi, this is really cool. I like the structural approach that you took here, but in lots of Python code, it's common to narrow types based on like the results of is instance checks or identity or equality checks. Are you doing any of that? Because like if I compare a type equal to, or if I compare a value equal to some other value, it's not really useful to know whether it supports a dunder-eq method, but rather what the right-hand side is so that I can narrow appropriately.
Yes, so what you mentioned is actually a future research direction that I'm considering. So one of the future research directions that I mentioned is, adding QuaC onto an LLM. Another research direction is adding the framework of QuaC onto something like MyPy, which supports the type narrowing, the branch-sensitive type prediction that you've discussed. So it's definitely a future research direction that I'm considering.
Cool. And then I also really like the way that you're querying attributes on like a database of known classes. Have you considered using that to like detect typos and method names and things like that, where a type is close except for a very near method?
So I guess that is a very interesting direction of future work, and I see potential with that being integrated with the LLM symbolic type inference method that I suggested, because sometimes those typos, we could leverage the capability of large language model to understand natural language cues in that scenario.
Thank you.
You're welcome.
Any more from the audience?
I have one question.
Okay.
So
Sorry.
I was wondering, is there, did you look at the soundness of your type inference? Like, can there be cases where you're losing the soundness of the inference?
So right now, what I'm doing is a simple information retrieval technique. So I'm not explicitly considering the soundness in this scenario, but it works quite well in practice, as we have demonstrated in our experimental evaluation. But as I just suggested, a future direction of work would be to put this thing on top of MyPy. So in this case, after we make a prediction, we can use MyPy to check it. And that would bring, greater soundness guarantees.
Okay, thank you. Nice one.
Okay, let's thank Jifeng.